Hi there, G12 learners. Welcome to another awesome episode of Pisikaalaman. This is Ma'am Allen, and for today, we will discuss about electric flux and Gauss law. To be specific, at the end of today's episode, you will be able to calculate electric flux, use Gauss law to infer electric field due to uniformly distributed charges on long wires, spheres, and large plates. And lastly, solve problems involving electric charges, dipoles, forces, fields, and flux in contexts such as but not limited to systems of point charges, electrical breakdown of air, charged pendulums, electrostatic inkjet printers. But before we begin, let us have a short recap of what we have discussed last episode. Do you still remember the following quantities and equations? Try to complete the table by writing your answers on your notebook. Let's find out if you get the correct answer. If you get all this in your mind, great job! In the previous lesson, we learned that the number of lines per unit area is proportional to the magnitude of the electric field. We also call that lines as flux density. In a uniform electric field, both in magnitude and direction, penetrate a surface area A, which is perpendicular to the field as shown in the illustration. The total number of lines penetrating the surface is proportional to the product of electric field E and area A. We call this product as electric flux. We use the symbol Greek letter phi for electric flux. Therefore, the equation for electric flux is equal to electric field multiplied by the area. Since electric field is a unit Newton per coulomb and area has a unit meter, therefore the unit for electric flux is Newton meter squared per coulomb. Let's have an example. What is the electric flux through a sphere that has a radius of 1.00 meter and carries a charge of positive 1.00 microcoulomb at its center? Given the radius, which is equal to 1.00 meter, charge of positive 1.00 microcoulomb, the electrostatic constant, and the area of a sphere, we find the electric field first. Using the equation, electric field is equal to K multiplied by Q over R squared. We substitute the value of R, Q, and K. Then we get the value for electric field, which is equal to 8.99 times 10 raised to 9 Newton per coulomb. Then we solve for the electric flux using the equation electric flux is equal to the electric field multiplied by the area. Substituting the values of electric field and area, we get the answer electric flux is equal to 1.13 times 10 raised to 5 Newton meter squared per coulomb. But not all electric fields cross an area that is always perpendicular to the surface or to a flat surface. Electric fields also form in an irregular shaped objects such as curves. In the given illustration, the electric field is passing through a surface area that is not perpendicular. If the surface is not perpendicular to the field, we consider the angle theta normal to the surface area. The number of lines that cross the area is equal in and out of the surface, as denoted by A prime and A. Therefore, we can say that A prime is equal to A multiplied by the cosine theta. We then conclude that the electric flux through A is equal to the electric field multiplied by area prime. Or we can substitute the value for area prime. Therefore, electric flux is equal to electric field multiplied by the area cosine theta. The flux through a surface area has a maximum value if it is perpendicular to the field. That means angle theta is equal to 90 degrees. When normal surface parallel to the field, angle theta is equal to 0 degree. Therefore, the flux is 0. If a positive point charge Q is located at the center of a sphere of radius r, the field lines is directed radially outward, hence perpendicular to the surface at every point. That is, at each surface point, electric field E is parallel to the vector delta A, meaning electric flux is equal to the electric field multiplied by delta A, or the change in area. If the surface is curved or the fields are not constant, you have to perform an integration. Closed surfaces of various shapes can surround the charge, as shown in the illustration. The flux through all other surfaces, denoted by capital letter S, are the same. These surfaces are called Gaussian surface. The Gaussian surface of a sphere has an electric field which is equal to the charge at a given area all over 4 pi epsilon sub 0, or the permittivity of free space multiplied by r squared. While the Gaussian surface of a cylinder has an electric field which is equal to the lambda all over 2 pi epsilon sub 0, or the permittivity of free space multiplied by r. The relationship between the net electric flux through a closed surface, or also known as Gaussian surface, and the charge enclosed by the area is known as Gauss law. Gauss law is a form of Maxwell's equation, the 4 fundamental equations for electricity and magnetism. It states that the flux of the electric field through any closed surface is equal to the net charge enclosed, Q, divided by the permittivity of free space, or epsilon sub 0, which is equal to 8.85 times 10 raised to negative 12 coulomb squared per Newton meter squared. Think of any application of Gauss law in your daily life. Write it on your notebook and share it to your classmates next meeting. That would be all for today. I hope you learned a lot in our today's episode. See you again next time and have a great day.